All right, these last two videos are pretty short, other applications of logarithms. So Newton's law of cooling is a model, and the model looks like this. T of t is equal to a e to the kt plus capital T sub s. All right, so what we've got right here is a model, and here in this model, t is going to be time. Maybe it's hours, maybe it's minutes, maybe it's days. It really just depends on the application. So T will be some kind of unit of time. Capital T, right? This is the temperature. And again, it could be in Fahrenheit or Celsius. After T units of time. A is the difference between an object and the ambient temperature. So we'll model like how an object cools. Like if we take something out of the oven, what does its temperature look like over time? And the ambient temperature would be your room temperature, okay? A is going to be the difference between the object's initial temperature and ambient temperature. And again, it's called Newton's law of cooling, but it could also be called Newton's law of heating, right? If I take something out of the fridge and put it in the room, it will warm up, all right? All right, and finally, K is a constant. And it's a constant that has to do with like the growth or the decay of the object and its temperature. But we're not gonna talk too much about the description. We will, however, have to find it. And that's finding it going to be similar to some of the other stuff we've done today. All right. So got example 6. Some coffee. So in this case, that's going to be our object. Some coffee was forgotten about. Somebody didn't get to eat their coffee. Hopefully they weren't grumpy. Some coffee was forgotten about and was initially 180 degrees Fahrenheit when it was made. After 15 minutes, in a 72-degree room, the coffee cooled to 150 degrees Fahrenheit. All right. So it started out 180 degrees. We made the coffee, set it on the desk, forgot about it. Room is 72 degrees Fahrenheit. Right. And after 15 minutes, coffee is now 150 degrees Fahrenheit, okay? So we're going to use Newton's law of cooling. Just remember, Newton's law of cooling is T of t equal to a e to the kt plus capital T sub s. So part A is going to be write a formula that models this. So again, we didn't specify what unit of time we have to do. 15, that could be a quarter of an hour. We could have t be in hours, and 15 would be 0.25. We could have t be in minutes, and then 15 minutes would be when t is 15. It's your choice, okay? So anyway, we just have to utilize all of our information. So we go back to our formula, right? Our formula, which is on the other side of the page, says T sub s. Oh, I didn't tell you what T sub s was. T sub s is the ambient temperature. I'm going to go ahead and fill in another bullet point. Ambient temp. So T sub s is the ambient temperature, and A is the difference in temperature between the object initially and the ambient temperature. Right? So A is the difference between the object initially, which is 180, and the ambient temperature, which is 72. So our A value right here is going to be 108. T sub s is that ambient temperature, which we just said the room is 72 degrees. K, we don't know K. We're going to have to find it. So we know that T of t is going to equal A, which is 108, times e to the kt, we don't know that, plus T sub s, which is 72 degrees. So we need to find K. And just like in the first video of this section with radioactive decay, we're going to use a point. We're going to use information to find what that K value is. So we know, right, that after 15 minutes, the coffee was 150 degrees Fahrenheit. So when T is equal to 15, the coffee is 150. We can write T of 15 is equal to 150. 150, that becomes our left-hand side. Got 150. It's equal to 108, e to the k. Still don't know k. And this is when t is 15 minutes. Plus 72, solve this exponential for k. We've solved a lot of exponential functions here today. That's why we did 6.6, all right? So subtract over that 72. We're going to get 78. When you subtract it over, equals 1 over 8 e to the 15k. We need to isolate the exponential, so we need to divide by 108 as well. 78 over 108, I'm not going to simplify that, but you could. E to the 15k. Take the natural log of both sides. So the natural log of the left-hand side looks like this, which again could be simplified. The natural log of the right-hand side, they're inverse functions. That's why we take the natural log of both sides. They undo each other, and we're just left with that exponent. Divide by 15, and we'll have our k value. All right. And yeah, actually, let's simplify this, right? 78 over 108, they're both divisible by 2. That's going to be 39 over 54. Both divisible by 3. That's 13 over 18. So k is going to be the natural log of 13 over 18 divided by 15. This is our k value. And we now have our formula. So our formula says T of t is equal to A, which we said was 108, times e to the k, which is natural log of 13/18, divided by 15, times t, plus 72. And this models our coffee temperature after t minutes. So we can use this. All right, we can use this to ask, what am I going to ask? How long until the coffee is 100 degrees? So start out at 180 degrees. Part B is going to be how long until the coffee is just 100 degrees. You don't want to drink 100 degree coffee, by the way. 100 degrees Fahrenheit, not a good temperature for coffee. Like warm coffee. So again, this is when is the temperature equal to 100 degrees. So you plug that in for your left-hand side. You get 100 is equal to 108 e to the ln of 13 over 18t divided by 15 plus 72. And again, you have to solve another exponential equation for t. So subtract 72 again, and we're going to get 28 equals 1 over 8 e to the ln of 13/18 over 15t. Divide by 108, take the natural log. Again, we're doing all of these very similarly to each other. 28 over 108 is equal to e to the ln of 13/18 over 15 times t. Take the natural log of both sides to get the natural log of 28 over 108. Undoes the exponential. We're just with the natural log of 13/18 over 15 times t. Now to solve for t, we'll multiply by the reciprocal. We're going to get that t is equal to the natural log of 28 over 108 times the reciprocal, which is 15 over the natural log of 13/18. And here we're going to approximate. And you might wonder, why did we not approximate the k value? And why are we approximating here? And the idea is that you never want, not never, but in a math class, you usually don't want to approximate until the very end. Because if you approximate in the middle and then approximate again, and then approximate again, you have compounding rounding errors, okay? Whereas here we can get as close to the right answer as possible. So at this point, you're just going to evaluate it with a calculator. And so you're going to get the natural log of 28 over 108 times 15 divided by the natural log of 13 over 18. And you're going to get about 62.22. All right. And what's our units? Was T in minutes, hours? It was in minutes. So a little over an hour. If you leave your coffee out for a little over an hour, it's going to be that 100-degree warm, gross coffee. I don't like coffee in the first place, so I think all coffee is gross, but even coffee lovers probably won't like this, although some people may still drink it for the caffeine. All right, so about 62 minutes. All right, and we can look at this. We can look at a graph of this, right? So if we looked at a graph of this, our function was 108 times e raised to the natural log of 13 over 18 t divided by 15 plus 72 is our function. And let's look at the first 65 minutes of this function. Started at 180 degrees, and then the ambient room is 72 degrees. So this is how it works, where our x-axis is our actual t-axis, that's minutes. Up here is the temperature. So notice, of course, this is like exponential change. When it's really hot, it changes very quickly. Eventually, it changes kind of slowly. You'll notice, right, that that we are about at 100 degrees right here after 62 minutes. And you can zoom out a little bit as well. And notice that as time goes on, it gets very close to that ambient temperature. It's going to get very, very close to 72 degrees. This is like almost 4 hours in, right? It's almost 72 degrees. Okay. All right. And that's Newton's law of cooling.